Generative AI applications are forcing engineering teams to support two distinct categories of data simultaneously. On one side, you have the absolute precision of structured records. On the other, the messy, unstructured language of human users. For decades, we've optimized systems for operational data. These are the transactions, user IDs, strict permission constraints, and audit trails keeping businesses running. They rely on rigid logic and exact correctness. Knowledge data operates differently. It lives in unstructured manuals, company policies, internal documentation, and chat transcripts. It is defined by nuance, context, and variable human phrasing. Traditional relational database architectures are built for the former. They operate on exact match binary logic. They execute commands perfectly, provided you know exactly which keywords to search for. Modern applications do not receive predictable commands. A user interacting with an AI assistant rarely asks to select a specific row from a table. They ask intent-driven questions, expecting the system to infer what they mean. When an architecture cannot bridge the gap between strict, exact match rules and abstract semantic intent, AI features become fragile. They either fail to return helpful information entirely, or they bypass security controls and return data that users are not authorized to see. Consider a typical customer support scenario. A user opens a chat window and types, "Why does my card keep getting rejected overseas?" When a traditional relational database tackles that question, the system executes a string matching command, searching for a specific phrase like international payment. Because it demands an exact match, the query misses relevant documents entirely, resulting in 0 rows returned. The system failed because human phrasing is highly variable. The user typed overseas and rejected. The official documentation used the terms international and authorization decline. The binary query logic could not recognize that both phrases describe the same concept. Relying on keyword indexing to power intent-driven retrieval creates massive blind spots. You cannot anticipate every synonym a user might choose, and guessing keywords guarantees your system will miss vital context. To solve the phrasing problem, developers use external embedding models. These models act as a translation layer, converting unstructured language into a strict mathematical structure. An embedding model takes a chunk of text and generates a vector, a high-dimensional array of numbers that mathematically represents the specific meaning and characteristics of that text. These vectors are incredibly dense. Systems like MariaDB can support up to 16,383 distinct dimensions for a single vector, capturing microscopic nuances and meaning. In this 3D space, embedding models mathematically force semantically similar ideas to cluster together. Vector search exploits this geography. The database embeds a user's question into a new point, then calculates proximity, expanding a radius outward to find the nearest stored points. This spatial calculation bypasses string matching entirely. The database no longer checks if letters align. It checks if concepts are close to one another, successfully capturing abstract human intent. Instead of binary pass or fail filtering, this multidimensional radius search retrieves content based on sliding scales of relevance. Translating messy text into precise coordinate geometry gives databases the ability to execute semantic search reliably. This retrieval mechanism is the engine behind Retrieval Augmented Generation, or RAG. Before an LLM generates a response, the application queries a database to fetch private, contextual data to feed into the model's prompt window. Let's return to the card decline question. The vector search works perfectly. By calculating proximity, it locates highly relevant paragraphs from an international authorization playbook, matching the user's intent exactly. But as this document layout shows, the retrieval contains a fatal flaw. The operational metadata attached to this playbook explicitly restricts it to internal Tier 3 support staff only. It is not meant for a public-facing chat application. Pure, specialized vector databases are built to calculate mathematical distance. They are often inherently blind to business logic, tenancy boundaries, and user authorization rules that live in separate operational systems. Passing raw semantic relevance to a large language model without checking relational permissions first exposes internal documents to unauthorized users. It creates an unacceptable enterprise data leakage risk. To prevent this, developers need a way to combine vector proximity with strict operational filtering. MariaDB version 11.7 solves this by natively integrating vector search capabilities directly into a traditional relational database environment. Look at the schema table. Developers add a dedicated vector n column directly alongside standard relational fields. This enables a single SQL query that orders results by vector distance, while simultaneously applying a traditional where clause to filter restricted access levels. The database evaluates both conditions together. It mathematically ranks the semantic relevance of the documents, while forcefully excluding any rows the current user does not have permission to view. Teams can even implement advanced techniques like reciprocal rank fusion, which mathematically balances semantic relevance against exact term matching when specific keywords like error codes are required. The system enforces these strict access parameters at the data layer. Non-compliant context is stripped out of the results before the information is ever passed to the external LLM. Relational governance provides the mandatory adult supervision that vector math lacks, making enterprise-grade AI applications secure. Systems engineers currently face a major architectural decision. Do they extend a unified relational database, or do they adopt specialized vector microservices? This diagram maps out a standard dual-flow architecture. An operational database manages the metadata and permissions while constantly executing a complex synchronization process to push updates over to a separate, dedicated vector database. Splitting the data creates immediate systems friction. Engineering teams must build external connectors, account for replication lag, and monitor for identity drift between two isolated environments. The most common failure mode in this setup is the creation of orphaned embeddings. If an internal document is deleted from the operational database, but the sync tool drops the request, the separate vector database will continue retrieving that deleted document for the AI model. A unified architecture eliminates this problem entirely. When vectors live next to metadata, a sol SQL deletion command instantly removes the relational record and the vector array in one guaranteed transaction. Specialized vector databases remain highly effective tools, particularly for extreme hyperscale retrieval workloads, where semantic search is the sole primary function of the application. But for the vast majority of engineering teams, unifying vectors and relational data drastically reduces pipeline failure modes and lowers overall operational overhead. Application design is shifting rapidly. Users expect interfaces to process open-ended, meaning-based questions rather than requiring precise, structured commands. Generating mathematical vectors solves the language problem, but those vectors are functionally useless in an enterprise environment without the operational context surrounding them. By keeping these technologies in one system, development teams can use their existing SQL expertise to build complex semantic search pipelines without needing to learn entirely new query models. The defining characteristic of a truly AI-ready database is its capacity to compute mathematical meaning within the strict enforcement of absolute relational truth.